Welcome back. In this video, we're gonna continue to solve the second problem in the bit manipulation series of this data lab. This question is called getByte. I copied the same problem description on the left side here from the source code. The function takes two inputs. The first is x is an integer, which we can always assume is a 32 bits integer. Then the second one is n, and n can range from 0 to 3. N basically means the particular byte we want to extract out of the x at position n. Let's take the same example here to further explain this. So given this number, remember this, each of these digits represent 4 bits, and then 1 byte is 8 bits, right? So if let's say if n is 0, it means that we want to extract the last two, the last bytes here, which are the last two digits of this number. In total, there are 8 digits. Each of them are 4 bits, so it's a 32 bits of integer. If n is 1, it means we want to extract these 2 digits. Similarly, if n is 2, then we want to extract this, right? So let's still use n equal to 1. Let me highlight this 2 digit that we will want to extract. So to extract this, a technique we can use, a straightforward way to think about is to apply some type of filter that only extract out these 2 digits, and all the others we just want them to be 0. We don't care about them, right? An easy way to do that is by applying a bit level AND operation with the number of like this. Here it basically means all the other positions we don't care. We just want to always zero it out. And then with this 2 digits as 1, sorry, not 1 actually, FF. So each digit is F. Here is F means 1111 in its bit representation, binary representation. When we do the bits AND between these two numbers, what we get is a number like this. Sorry, 0005600. Again, these are the two numbers we really want to keep. All right. This is something we call a mask. This is very fundamental idea and very handy technique we use very frequently in almost all the bit manipulation type of problems. Later on in other bit manipulation related questions, we will frequently use these techniques. So now we have this number, intermediate number that have the particular 2 digit we want. In order to get a final answer, we also need to shift these 2 digits to the right, right? So we can shift it to the right by 8 bits. Here it's 8 because we have 2 zeros here. Each 0 is 8 bits of 0. So this 8 really is determined by number n, where when n is 1, we shift it by 8, right? If n is 2, that's when we want to extract this 2 number. So we need to shift it by 16 bits in that case, right? Cool. So once we do the right shift here, then what we have is really just this number of 56, and then this is equivalent to the same number of, we don't need to write all the zeros in front. So this is the actual result we want to get here, right? From a high level, very straightforward idea here, right? Before you jump into code, there are actually another kind of constraints or 2 constraints we need to consider. Constraints number 1, in the source code of the bits.c file, it actually mentioned that we cannot use large number like this. The largest number, integer constant number here we can use is only 0x ff. So we cannot use number larger than 0xFF here, actually constant number or integer. That's one aspect. The other aspect is even if we can use a large number, here this mask is actually a dynamic mask here. What I mean by dynamic is where these two FF present, it really depends on the number n. So here, like we need, if n is 1, then FSS should be here. But if n is 2, then this 2FF should be really in the position here, right? So the way we can generate this mask dynamically is actually applying the left shift by the same number of 8 to this FF as a base mask. Right? We will see how to do that later in the coding. The second thing of the second constraint here is like we cannot do this multiply operations. The only legal operations here are this here, which does not have the multiplier here, right? So cannot use multiply. The good thing is like here we always multiply a n by 8, no matter what n is here. And then if some number is a time by 8 here, the handy way to do that is actually n times 8 really equal to n shift left shift by 3. This is because every time we shift to the left by 1 position, we multiply the number by 2. And then 8 is really 2 to the 3 here, right? So we shift to the left side by 3 times. We get the same effect of apply by n multiply 8 here. Cool. With that, we can start coding. Okay, here I have my terminal open. Remember, the first thing we want to do is actually to generate a mask. Let's check out. Come back to here again. So here to generate this mask dynamically by the number n. So we want to shift this FF to the left by a number that's determined by n. In this case, if n is 1, we want to shift it to the left by 8 bits. This number is exactly the same number here that later on we want to shift the intermediate result to the right. Let me first define something called, let's say, shift number. This basically means equal to n times 8. I remember earlier we were saying like this times 8 is actually not allowed because we are not allowed to use the multiplier operators. We can equally achieve the same thing by left shifting n to 3 times. This is basically equal same as times 8. And then now we can generate the mask, which is 0.5 to the left side of shift numbers. And now we can generate result now by apply the bit level operator between x and the mask, plus we also need to the last step is to shift it to the right side to the by the same number of shift here. Okay, let's give it a try. Sorry. Okay, let's give it a try on the left side. Make b test. Cool, and then let's give it a try to test this specific function called getByte. Okay, actually not correct because giving us some error here. Let's look at an error here. So given this particular input, it is expecting a hexadecimal number of 80. In fact, we are returning this negative number with all the FFF in front of this number. What is causing this? Let's take a look at this. Here, the problem happens actually in the right shift. You see, if the input number of x is a negative number, that basically means the leftmost bit is 1. In this case, it starts 1. Number 8 here basically means it's a binary representation. It's a 1 0 0 0. So the left side is 0. And after we apply this mask, and then we shift it to the right side, this red shift is actually a logical shift. So it will backfill the left side by 1 instead of by 0. What we want is actually on the left side is all 0. So a quick fix for this is to uh, apply another mask at the end. This new mask is just this FF. Um, sorry, here. What this means is like I only want to whatever this number is. I don't care the left side of the number. We only want the rightmost 8 bits, and then all the others will be 0, right? So let's give this a try. Okay, now everything passed here. Cool. Before you call this a victory, remember we also need to use this DLC to check the results. So we want to see how many operators we are using right now. So it's bits.c. Okay, so getByte, right now we are using 5 operators to achieve the right results. Maximum is 6, so it's not too bad. If we want to leave it here, we can call it a victory. But is there a better way to do this? So, let's look at where we are using our operators, right? So in order to generate the mask, we first need to shift this FF to the left side, apply this mask with the number, and then shift it back to the right by exactly the same number of steps here. And then finally, we need to apply another base mask here. How about we just do not shift the mask left and then shift the number back here again? Is there a way for us just directly shift the what about if we just shift the input number X to the right side by the same shift number here? Will that save us something? So what I mean by that is, let's see. So V2 thoughts. Here, instead of applying this root number directly with the mask, how about we shift it to the right side first? And then this will give us, so after we shift it, this will be something like this, right? And then at this point, we apply a mask just as fx. And in this case, this mask is static. We always want the right 8 bits here. And then this just give us whatever we want here, right? The beautiful thing about here is also a beautiful thing here is it always apply 0 to on the left side here. So no matter the input number, whether it's a positive or negative number, we always get the left side all as 0. So let's give this a try. Let me comment out this part as V1 solution. Okay, now V2. So we have the same shift number as N left shift 3, and then we return. We do the shift on the X and then apply mask. Will this work? Let's see. Oh, sorry. This should be a typo here. Okay, and then yep, it works. So it's logically it's the same thing. How many operators we are using now? So now we reduce our number of operators from 5 to 3 here. So yeah, this is definitely a more optimized solution than the first one. The reason I want to bring up this first solution here, first is like it is a little bit more intuitive the first time we think about this problem, and also it makes this concept of mask a little bit more obvious. This is a very useful technique in all bits manipulation problems. We will run into situations where we use mask a lot later in the other problems. Okay, with that, we are done with this problem. We'll see you in the next question.